Welcome to this video where we discuss the solution of linear Diophantine equations in two variables. These are equations ax plus by equals c, where a, b and c are integers, and we're looking for solutions x and y that are also integers. First, we recall that the set n denotes the natural numbers or the positive integers, and the set z denotes the integers in general. We need to understand what it means for a to divide b when a is not equal to 0. We say that a divides b if the equation ax equals b has a solution in the integers. That is, there exists an integer t such that at equals b. Note that for all integers d, we have 1 divides d. And this is because the solution to the equation x equals d is x equals d itself. If a divides b, then the quantity b upon a is an integer. Since a divides b, there exists an integer t such that b equals at, and this means that b upon a, which equals t, is an integer. We can use divisibility to show equality. Say we have two natural numbers c and d such that c divides d and d divides c. Then it follows that c equals d. Since c divides d, there exists a natural number t1 such that d equals ct1. And since d divides c, there exists a natural number t2 such that c equals dt2. This means that c, which equals dt2, is equal to c t1 t2. And this implies that 1 equals t1 t2. Now since c and d are both positive, this means that t1 equals t2, which equals 1. Hence c equals dt2, which equals d. A short corollary to this is that if d is a natural number that divides 1, then d is equal to 1. We know that 1 divides d for all integers d, and we also have that 1 is a natural number. So combining this with d divides 1 gives d equals 1. We simply take c equal to 1 in the previous lemma. Now we discuss some properties of divisibility. Namely, the first property that we look at is that it's a transitive relation. If a, b and c are integers with a and b not equal to 0, and a divides b and b divides c, then a divides c. Since a divides b, there exists an integer t1 such that at1 equals b. Also, since b divides c, there exists t2 such that bt2 equals c. So c equals bt2, which equals at1 t2. Now t1 t2 is also an integer. This means that a divides c. Also, if a is an integer not equal to 0, we have that a divides the modulus of a and the modulus of a divides a. If a is greater than 0, then the modulus of a is equal to a, and so the equation mod a x equals a has solution x equals 1. Thus mod a divides a. Also, the equation ay equals mod a has solution y equals 1. Thus a divides mod a. If a is negative, then mod a equals negative a. So the equation mod a x equals a has solution x equals minus 1. So mod a divides a, and the equation ay equals mod a has solution y equals minus 1. So a divides mod a. In both cases, we have that a divides mod a and mod a divides a. The division algorithm states that if we have two integers a and b with a not equal to 0, then there exist unique integers q and r such that b equals aq plus r, where r is greater than or equal to 0 and less than mod a. So this statement is composed of two smaller statements. One is a statement about existence and one is about uniqueness. First, we start with the lemma. If we have a non-empty subset of the non-negative integers, then it must contain a least element. And the proof is that if it did not have a least element, we could always find a smaller element. In particular, we could find a smaller element than 0, but 0 is the least non-negative integer, and this is a contradiction. Because 0 is a lower bound for the set, and no element can be lesser than 0. There's another important fact that we have to look at, which is the Archimedean property. So it says that given an integer s and a natural number t, there exists a natural number k such that tk is greater than s. Again, we prove this by contradiction. We know that k is less than or equal to tk for all natural numbers k. Assuming that tk is less than or equal to s for all natural numbers k implies that k is less than or equal to tk, which is less than or equal to s for all naturals. This means that s would be bigger than or equal to every positive integer, again a contradiction. There's also this special property of the modulus function. For all integers b, we have that b plus mod b is greater than or equal to 0. If b is non-negative, then mod b equals b, and so mod b plus b equals b plus b, which equals 2b, which is greater than or equal to 0. If b is negative, then mod b equals negative b, and b plus mod b equals b minus b, which equals 0. We can start to look at what the set of all multiples of an integer means. Let a in z be an integer. Then m of a denotes the set of all multiples of a. If a is equal to 0, then m of a is the singleton 0. If a is not equal to 0, then the set of all multiples is infinite. In particular, it contains the elements negative 2 mod a, negative mod a, 0 mod a, 2 mod a, and so on. And note that the only multiple of a in between negative mod a and mod a is 0. Now we look at the proof of the division algorithm. Take two integers a and b, where a is not equal to 0, and consider the set R such that its elements are b minus ax, where x is an integer and b minus ax is non-negative. Choosing different values of x produces different elements in the set, as long as b minus ax is non-negative. We claim first that this set is non-empty. We know that mod a is a natural number, hence there exists a natural number t such that mod a t is greater than mod b. This follows by the Archimedean principle. If a is positive, then mod a equals a, so at is greater than mod b. And if we take x equal to minus t, we have b minus ax is equal to b minus a times negative t, which equals b plus at, which is greater than b plus mod b, which is non-negative. So b minus a into negative t is an element present in R. If a is negative, on the other hand, then we have mod a equals negative a, hence negative at is greater than mod b, and now we take x equal to t. Whence we arrive at b minus ax equals b plus negative at, which is greater than b plus mod b, which is non-negative. So b minus at is an element in R if a is negative. In either case, if a is negative or positive, we can find at least one element in R, and a equals 0 has been excluded. We are not considering the case of a being 0. So all this goes to show is that R is a non-empty subset of the non-negative integers. This means that R has a least element. So we can set little r equal to the minimum of R. It is obvious that R is non-negative. We claim that R is less than mod a. Let x equal q be the value of x that achieves the minimal element of R. So R is equal to b minus aq. For the sake of contradiction, assume that R is greater than or equal to mod a. This implies that R minus mod a is non-negative. Also, R minus mod a is less than R, because mod a is positive. Now we always have that mod a is plus or minus a depending on whether a is positive or negative. If a is positive, then mod a equals a, And so r minus mod a, which equals r minus a, equals b minus a cube minus a, which equals b minus a times q plus 1, which is non-negative, because we assumed that r was greater than or equal to mod a. So if we take x equal to q plus 1, we find that b minus a times q plus 1 is non-negative and it's equal to r minus mod a, which means it's less than r. This means that b minus a into q plus 1 is an element of r that is less than r, contradicting the minimality of r. So if a is positive, r has to be less than mod a, which equals a. We cannot have the case that r is greater than or equal to mod a. Similarly, if a is negative, then mod a equals minus a, and assuming mod a is less than or equal to r gives another contradiction. We have r minus mod a, which equals b minus a cube plus a, which equals b minus a times q minus 1, which is non-negative. Again, because we assume that mod a is less than or equal to r. And if we take x equal to q minus 1 this time, we get that b minus a into q minus 1 is non-negative, and since it's equal to r minus mod a, it is strictly less than r. So b minus a into q minus 1 is another element of r that we can find that is less than r, and this is a contradiction because it contradicts the minimality of r. So again, even if a is negative, we must have that r is less than mod a. So the existence of an r that is non-negative and less than mod a has been shown, and from the existence of this r, it also implies the existence of a q such that r equals b minus a q, and just rearranging we get that b equals a q plus r. This is true if a is positive or negative. Now the only part that is left to prove is that this q and r are both unique. Assume that there exists a second pair of r and q satisfying the same conditions. Label them r prime and q prime. So the first condition was that r prime must be non-negative and it must be strictly less than mod a, and q prime is an integer where q prime satisfies the equation b equals a q prime plus r prime. Then we have that b equals a q prime plus r prime, and it also equals a q plus r. Rearranging, this gives that a multiplied by q prime minus q is equal to r minus r prime. Now a is non-zero and q prime minus q is an integer. This means that a divides r minus r prime. Also, r is non-negative and less than mod a, and negative r prime is non-positive and strictly greater than negative mod a. From this it follows that r minus r prime is strictly greater than negative mod a and strictly less than mod a. In other words, r is a multiple of a in between negative mod a and mod a. And we showed earlier that since a is not equal to 0, r minus r prime must be equal to 0. From this it follows that r equals r prime, which also ultimately leads to the fact that q equals q prime, because aq plus r is equal to aq prime plus r prime. Cancelling off the r and r prime, which are equal, gives aq equals aq prime, and since a is non-zero, we get that q equals q prime. Thus we have proven the uniqueness. If there is a second pair q prime and r prime, then r equals r prime and q equals q prime. So they must be the same pair. Now we move on to the concept of the greatest common divisor. Take two integers a and b, not both 0. Then the GCD of ab is d, which is a positive integer such that d is a common divisor of a and b. So d divides a and d divides b. And if an integer c is also a common divisor of a and b, that is c divides a and c divides b, then we must have that C divides the GCD of A and B, which is D. There's yet another definition which says that two numbers that satisfy the equation GCD of AB equals 1 are said to be coprime. We start looking at some properties of the GCD of A and B. The first lemma that we look at is that if D equals the GCD of A and B, then for all integers x and y, we have that D divides AX plus BY. We know that D is a common divisor of A and B, so D divides A and D divides B. This means that there exist integers t1 and t2 such that A equals dt1 and B equals dt2, and taking arbitrary x and y, which are integers, we have that ax plus by equals dt1x plus dt2y, and factoring out the common factor of d, we get that equals d multiplied by t1x plus t2y. But t1x plus t2y is an integer, so this means that d divides ax plus by. In other words, what we have shown is that d, the greatest common divisor of a and b, divides every integral linear combination of a and b. We have a special case. If a and b are integers where a is not equal to 0 and a divides b, then the GCD of a and b equals mod a. The proof goes like this. Mod a is strictly positive and mod a is a natural number. Also, mod a divides a and mod a divides b. So mod a is a common divisor of a and b. If c is another common divisor, then c divides a and c divides b. That is the definition of a common divisor. But a divides mod a, and by the transitive property of the divisibility relation, we have c divides a and a divides mod a, and so c divides mod a. So mod a satisfies the definition of the GCD of a and b, and so mod a is the GCD of a and b. The next theorem states that if d equals the GCD of a and b, then there exist integers x and y such that ax plus by equals d. Consider the set L whose elements are as plus bt, where s and t are integers, and as plus bt is greater than 0, with the condition that a and b are not both 0. So L, in other words, is the set of positive integral linear combinations of a and b. It is easy to see that L is a non-empty subset of the non-negative integers. We just have to choose s and t wisely enough to find elements that have to lie in L. This means that L has a minimal element, and we claim that the minimum of L is equal to the GCD of a and b. Let C equal the minimum of L, and let S equal x and t equals y be the values of s and t that achieve the minimal element. So C equals ax plus by. C is an integral linear combination of a and b, which is positive. Also let D equal GCD of a and b. Earlier we proved that D divides every integral linear combination of a and b. So that means that D divides ax plus by, which equals C. Now we also show that C is a common divisor of a and b. We know that C is non-zero, so we can divide A by C using the division algorithm. There may be some remainder. So A equals CQ plus R. Since C is positive, mod C is equal to C, and so R has to satisfy the condition of being non-negative and strictly less than C. We have to now use this fact to show that the remainder is equal to 0, from which it will follow that C divides A. Assuming R to be positive leads to a contradiction. We know that R equals A minus CQ, but C was equal to AX plus BY. So that means that A minus AX plus BY times Q is equal to R. And simplifying, we get that A into 1 minus QX minus BQY is equal to R. Now 1 minus QX and QY are both integers. So R is an integral linear combination of A and B. But if we make the assumption that R is positive, then R would be an element of L that was strictly less than C. And the fact that it has to be less than C follows from the division algorithm. So as we said that R must be an element of L less than C, which is the minimum element of L, and this is a contradiction. So R equals 0 is the only possibility. From the fact that R equals 0, we know that A equals CQ, and so C divides A, since C is non-zero. Similarly, it can also be shown that C divides B, because there was nothing special about A. So C is a common divisor of A and B. Thus, by the definition of the GCD of A and B, C must divide D. Now C and D are naturals, where C divides D and D divides C, and this means that C equals D. Or in other words, the minimum of L, which equals C, is equal to the GCD of A and B, which equals D. Unlike the case of the division algorithm, the representation of the greatest common factor of A and B as an integral linear combination of A and B is not unique. We have only proven that there exists an integral linear combination of A and B that yields the GCD of A and B. But to actually find such an integral linear combination, we need to make use of the Euclidean algorithm. Let A, B and X be integers with A and B not both 0. Then the GCD of A and B is equal to the GCD of A plus BX with B. This is a lemma that is true in general, and we will prove it now. Let the GCD of A and B equal D, and let the GCD of A plus BX comma B equal D naught. Then A plus BX is an integral linear combination of A and B. So D, which is the GCD of A and B, divides A plus BX. Hence D is a common divisor of A plus BX and B, because we knew from earlier that D divides B. And so by the definition of D naught, which is the GCD of A plus BX comma B, D must divide D naught. Similarly, A is equal to A plus BX minus BX. So A is an integral linear combination of the two integers A plus BX and B. So D naught, which equals the GCD of A plus BX comma B, divides A. So D naught is a common divisor of A and B, and so D naught must divide the greatest common factor of A and B, which equals D. Now D and D naught are both positive and are natural numbers. This means that D equals D naught, which implies that the GCD of A and B equals the GCD of A plus BX comma B. What this means is that adding a multiple of one number to another does not affect the GCD of A and B. Now take integers A and B, with A and B not both being 0. Without loss of generality, we can assume that A is non-zero. Then divide B by A using the division algorithm, and of course there may be some remainder. This gives that B equals AQ1 plus R1, where Q1 and R1 are the first pair of quotient and remainder. Your R1 is non-negative and strictly less than mod A by the division algorithm. Also, R1 is equal to B minus AQ1. So you can say that the GCD of A and B is equal to the GCD of A and B minus AQ1, but that is nothing but the GCD of A and R1. In other words, we have created a chain. We have created an equality between the GCD of A and B and the GCD of A and R1, the first remainder. And we keep going. If R1 is 0, then B is equal to AQ1, and so A divides B. And this means that the GCD of A and B equals mod A. But if R1 is positive, then we continue. We now divide A by R1, and so A equals R1 Q2 plus R2, where Q2 and R2 are the second pair of quotient and remainder, and R2 is non-negative and strictly less than R1. Here R1 is positive, so the modulus of R1 is equal to R1. This means that the GCD of A and B, which was shown to be equal to the GCD of A and R1, is now equal to the GCD of A minus R1 Q2 and R1, but A minus R1 Q2 is simply R2. So the GCD of A and B is equal to the GCD of R2 and R1. Again, if R2 is 0, we stop, otherwise we keep going, and we keep continuing till we get a remainder of 0. So to summarize, we have the following set of equations. B equals AQ1 plus R1, where R1 is non-negative and strictly less than mod A. A equals R1 Q2 plus R2, where R2 is non-negative and strictly less than R1, and so on. In general, the kth equation will be R sub k minus 2 is equal to R sub k minus 1 times Qk plus Rk, where Rk is non-negative and strictly less than Rk minus 1. And the very last equation will be R sub n minus 2, which equals R sub n minus 1 Qn plus Rn, where Rn is taken to be 0. And so the last non-zero remainder is R sub n minus 1. And the reason that this algorithm does indeed terminate is that there exists only a finite number of positive integers between mod A and 0. And each of the remainders is strictly less than the remainders that come before it. The last non-zero remainder, which is Rn minus 1, is the GCD of A and B. And to show this, we again resort back to the chain of equalities that we had created. Whether the GCD of A and B was equal to the GCD of A and R1, which was equal to the GCD of R1 and R2, which would be then equal to the GCD of R2 and R3, and so on. And continuing in this way, we get that it is equal to the GCD of R sub n minus 1 and R sub n. But R sub n was 0, and R sub n minus 1 divides 0, because any integer divides 0 except for 0 itself. So that means that the GCD of R sub n minus 1 and R sub n is equal to the absolute value of R sub n minus 1, which equals R sub n minus 1. Finally, we can use back substitution to express the GCD of A and B, which equals R sub n minus 1, in terms of a linear combination of A and B alone. And while earlier we showed that there does exist a linear combination of A and B that gives this GCD, we now have a way of actually finding this linear combination. And this is the first step to solving linear Diophantine equations. So let us take an example. First, we will express the GCD of 36 and 14 as a linear combination of 36 and 14, and so we will find a particular solution to the equation 36x plus 14y equals 2. We know just by heuristic calculations that the GCD of 36 and 14 is 2, but we will now show this using the Euclidean algorithm that we just discussed. So we begin the division process. So we have first the 36 equals 14 times 2 plus 8. Here 8 is non-negative and strictly less than 14. Then we divide 14 by 8 and we get a quotient of 1 and a remainder of 6. Then we divide 8 by 6 with a quotient of 1 and a remainder of 2. So we have 8 equals 6 plus 2. And finally, we divide 6 by 2 and get a quotient of 3 and a remainder of 0. 6 equals 2 times 3. So now studying these set of equations, we see that the last non-zero remainder is 2. And by the discussion that just occurred, it means that 2 is the GCD of 36 and 14. Now this GCD can be expressed as a linear combination using back substitution, which we will illustrate now. So first we rearrange all the equations except the last, that is 6 equals 2 times 3, in such a way so as to make the remainders the subject of the formula. So we'll just copy these 4 equations into the next slide. We have 36 equals 14 times 2 plus 8, 14 equals 8 plus 6, 8 equals 6 plus 2, and 6 equals 2 times 3. Rearranging the first equation, we have 8 equals 36 minus 14 times 2. The second one gives us 6 equals 14 minus 8, and the third gives 2 equals 8 minus 6. Now we substitute the first equation into the second into the third, and this will give us a linear combination of 36 and 14 that equals 2. Again, we copy the equations, we just rearranged. Starting with the last equation, we have 2 equals 8 minus 6, but 6 is nothing but 14 minus 8. So that gives that 2 equals 8 minus 14 minus 8. And simplifying, we have that equals 8 times 2 minus 14. Then we substitute the value for 8 from the first equation. So that gives 36 minus 14 times 2 multiplied by 2 minus 14. And simplifying, that gives 36 times 2 minus 14 times 5. And there we have it. The GCD of 36 and 14 is 2, which equals 36 times 2 minus 14 times 5. 36 times 2 is 72, and 14 times 5 is 70. And indeed, 72 minus 70 is equal to 2. And so a particular solution to the equation 36x plus 14y equals 2 is x naught equals 2 and y naught equals minus 5. Now we come to the all-important theorem that governs the solution of linear Diophantine equations. So we take integers a, b and c where a and b are not both 0 and let the GCD of a and b equal d. Then the equation ax plus by equals c has a solution if and only if d divides c. So to prove this, we first consider what happens if d divides c. If d divides c, then c is equal to dt, where t is some integer. It is known that there exist many solutions to x plus by equals d, which we proved earlier, because d is the GCD of a and b. And let x naught and y naught be a particular solution to x plus by equals d. So ax naught plus by naught equals d. Then we can multiply this equation on both sides by t to give atx naught plus bty naught equals dt, which equals c. This means that the equation ax plus by equals c also has a solution. And in particular, x equals tx naught and y equals ty naught is one such solution. Now to prove the converse, suppose that ax plus by equals c has a solution. Then c is a linear combination of a and b, and from this it follows that the greatest common divisor of a and b, which is d, divides c, and that completes the proof. Now we discuss how one can find a particular solution to ax plus by equals c, where c is not equal to d in general. Here by d we mean the GCD of a and b. So we take an integer c and we consider the equation ax plus by equals c. We know from the previous theorem that if d does not divide c, then the equation has no solution. So suppose that d divides c, then c equals dt for some integer t, and a particular solution x naught comma y naught to the equation ax plus by equals d can be found using the Euclidean algorithm. So this will give us ax naught plus by naught equals d. This gives ax naught plus by naught equals d. Hence we can obtain a particular solution to the equation ax plus by equals c. And this is done as follows. We simply use the solution to ax plus by equals d, which is x naught comma y naught, and multiply both sides by t. So this gives us atx naught plus bty naught equals dt, which equals c. And so tx naught comma ty naught is a particular solution to the equation ax plus by equals c. So let us look at an example of this. We'll try to find a particular solution to 36x plus 14y equals 6. Here c is equal to 6. We showed earlier that the GCD of 36 and 14 was equal to 2, and 2 does indeed divide 6. The particular solution that we found was 36 times 2 minus 14 times 5 equals 2. So x naught was equal to 2 and y naught was equal to minus 5. Now all that is left to do to find the solution of 36x plus 14y equals 6 is to multiply this solution by 3. This gives 3 times 36 times 2 minus 14 times 5 is equal to 3 times 2, which is equal to 6. This yields 36 times 6 minus 14 times 15 is equal to 6. So a particular solution is x naught equals 6 and y naught equals minus 15. Again, I repeat that a particular solution only existed because the GCD of 36 and 14, which is 2, divides 6, which is c. To find a general solution to a linear Diophantine equation given a particular solution, we still require 2 more theorems, which we will now go ahead and discuss. So say the GCD of a and b is d, then we claim that the GCD of a upon d, comma b upon d exists and is equal to 1. To show that the GCD of a upon d and b upon d exists, we need to show that a upon d and b upon d are integers and are not both 0. Since d divides a and d divides b, we definitely have that a upon d and b upon d are integers. Also, one of a or b must be non-zero for the GCD of a and b to be defined. And so the corresponding fraction a upon d or b upon d is non-zero. This means that the GCD of a upon d, comma b upon d exists. Now let d naught equal the GCD of a upon d, comma b upon d. Since ax plus by equals d has at least one solution, we can divide this solution by d to obtain a upon dx plus b upon dy equals 1. And since a upon d, comma b upon d are integers, this means that d naught, which equals the GCD of a upon d, comma b upon d, divides 1. Because the GCD of a upon d and b upon d divides every linear combination of a upon d and b upon d. But d naught is a natural number, and by one of the lemmas that we previously discussed, d naught, which equals the GCD of a upon d, comma b upon d, must in fact be 1. We can put everything that we just discussed all together to get a very important fact. If the GCD of a and b is d, and d divides a and d divides b, then there must exist integers u and v such that a equals du and b equals dv. This is evident from the fact that d is a common divisor of a and b. But what is more important is that u, which is equal to a upon d, and v, which is equal to b upon d, are both coprime. In other words, the GCD of u and v is equal to 1. Now the second theorem that we need before we can finally pass into the phase of finding a general solution to a linear Diophantine equation is that if two integers a and b are co-prime, that is if their GCD is equal to 1, and we have the condition that a divides bc, then we must have that a divides c. The proof of this is very simple. By hypothesis, we've assumed that a divides bc, and this implies that there exists some integer t such that at equals bc. Also, knowing that the GCD of a and b is 1 tells us that the equation ax plus by equals 1 has a solution. Let us call this solution x0, y0. So ax0 plus by0 equals 1, and so c, which is equal to c times 1, is equal to c times ax0 plus by0, and expanding that out we get c is equal to ac x0 plus bc y0, which equals ac x0 plus at y0, since bc is equal to at. And finally, pulling out the common factor of a from the right hand side, we have that c is equal to a times cx0 plus ty0. Now cx0 plus ty0 must be an integer. This means that a divides c, and that completes the proof of this theorem. We are finally ready now to find the general solution from a particular solution to any linear Diophantine equation. Let the GCD of a and b equal d, and let c in z be an integer. Also let x0, y0 be a particular solution to the equation ax plus by equals c. So in other words, ax0 plus by0 equals c. Then we define two sets. The first set, which we will call capital T, is defined as follows. It is the set of ordered pairs x and y, where x and y are integers, and x and y satisfy the two equations x equals x0 plus b upon dt and y equals y0 minus a upon dt, where t is some arbitrary integer. And the second set that we defined, capital S, is the set of ordered pairs x and y, where x and y are integers, and ax plus by equals c. So in other words, S is the set of solutions to the equation ax plus by equals c, and those solutions are of the form x, y. Then the theorem that enables us to find a general solution from a particular solution states that S, the set of solutions, is equal to T, and this is always true. As we said, S is the solution set and T is a generating set for S. So essentially what this theorem allows us to do is that it gives us an indirect means of generating the set S of solutions. We do not find S directly. Instead, we find the set T, and then using the theorem that T is equal to S, we can present T as a final solution to the linear Diophantine equation. Now to prove the theorem we just stated, we need to show two things. First, we need to show that every element in T is a solution to the equation ax plus by equals c. What this will mean is that T is a subset of S. Later on, we will then prove that S is also a subset of T, and then putting these two facts together, we will get that S is equal to T. So let us first show that T is a subset of S. Take T in Z to be an arbitrary integer and set X equal to x0 plus b upon dt and y equal to y0 minus a upon dt. Now consider the linear combination of a and b, which is ax plus by. This is equal to a times x0 plus b upon dt plus b times y0 minus a upon dt. And simplifying, we get first ax0 plus by0, and second the terms ab upon dt minus ab upon dt. And simplifying this, we know that ax0 plus by0 was a particular solution to ax plus by equals c, and so ax naught plus by naught is equal to c, while the other two terms cancel out to 0. What this means is that ax plus by for any integer t is equal to c. So every element in T is a solution. Next, we show that every element in S is some element in T. This will then prove that S is a subset of T. Because the GCD of A and B is D, there exists integers u and v such that A equals du and b equals dv. And as discussed earlier, the GCD of u and v is 1. Let x comma y be a solution to x plus by equals c. Then x comma y will be an element of S. This means that ax plus by equals c, but it also equals ax naught plus by naught, because that is a particular solution. And rearranging, we get that a multiplied by x minus x naught is equal to b multiplied by y naught minus y. But a was equal to du and b was equal to dv, and substituting these in, we get that du multiplied by x minus x naught is equal to dv times y naught minus y. And cancelling out the d, which is non-zero, we get that u multiplied by x minus x naught is equal to v times y naught minus y. Now y naught minus y is an integer, and this means that v divides the quantity u times x minus x naught. Also, the GCD of u and v is 1, so that means that v divides x minus x naught. In other words, there exists an integer t such that vt is equal to x minus x naught. Thus, x is equal to x naught plus vt, which equals x naught plus b upon d times t. Here we have simply rearranged the equation vt equals x minus x naught. Now we know that x is equal to x naught plus vt. Again, rearranging it, we get x minus x naught equals vt. And so u multiplied by x minus x naught, which was shown to be equal to v multiplied by y naught minus y, can be rearranged in the following way. On the left hand side, we have the quantity uvt, where x minus x naught has been substituted with vt, and on the right hand side, we have the same quantity, v multiplied by y naught minus y. Now cancelling off the v, which is non-zero, we get that ut equals y naught minus y, and so rearranging, we get that y equals y naught minus ut, which equals y naught minus a upon dt. So that means that the solution x comma y is of the form x naught plus b upon dt comma y naught minus a upon dt, where x naught comma y naught was a particular solution and t was some integer. But by definition, this ordered pair must be an element of T. And so we have shown that every element of S is an element of T, and that completes the proof. Lastly, we look at an example that applies all that we have discussed. We try to find a general solution to 36x plus 14y equals 6. We already did find a particular solution, which was x naught comma y naught equals 6 comma minus 15, and now we use this. Here a is equal to 36 and b is equal to 14, and the GCD of 36 and 14 was 2. So u, which equals a upon d, is equal to 36 upon 2, which equals 18, and v, which equals b upon d, which equals 14 upon 2, is equal to 7. So the general solution, as shown earlier, was x equals x naught plus b upon dt and y equals y naught minus a upon dt. B upon d was nothing but v and a upon d was nothing but u. And so, substituting this into the first equation, for x we get x equals 6 plus 7t and y equals negative 15 minus 18t. And this is true for all integers t. Now we can use these two equations that we have just derived, x equals 6 plus 7t and y equals negative 15 minus 18t, to generate a table of solutions for this equation. Here we can sample a few integers for t, such as negative 2, negative 1, 0 and 1, and we can see what the corresponding x and y values are. For example, when t is equal to 0, we get x to be equal to 6 and y to be equal to negative 15. This is the particular solution that we started out with, and when we take t equal to negative 1, we get x equal to negative 1 and y equal to 3. When t equals negative 2, we get x equal to negative 8 and y equal to 21. When t is 1, we get an x value of 13 and a y value of negative 33. And all these 4 pairs are solutions. It can be verified. For example, taking the solution produced when t is equal to negative 2, we get 36 times negative 8, which is the x value, plus 14 times 21, which is the y value, equals negative 288 plus 294, and this does indeed equal 6. And similarly, taking the x and y values produced by t equals negative 1, we get 36 times negative 1 plus 14 times 3, which is equal to negative 36 plus 42, and again we see that it equals 6. And in both cases, the solution is verified. So this goes to show that the method that we have derived is valid and it does indeed work. And I encourage you to try some examples of your own to see the true scope of this method.